Well, good morning, everyone. I want to welcome you to the Biostatistics for Biomedical Research, Session 3, which is our fun session on statistical graphics and statistical tables. I'm really glad you're here, and I'm just going to check. Well, good morning, everyone. I want to welcome you to the Biostatistics for Biomedical Research, Session 3, which is our fun session on statistical graphics and statistical tables. I'm really glad you're here, and I'm just going to check. Well, good morning, everyone. I want to welcome you to the Biostatistics for Biomedical Research, Session 3, which is our fun session on statistical graphics and statistical tables. I'm really glad you're here, and I'm just going to check. Well, good morning, everyone. I want to welcome you to the Biostatistics for Biomedical Research, Session 3, which is our fun session on statistical graphics and statistical tables. I'm really glad you're here, and I'm just going to check. Well, good morning, everyone. I want to welcome you to the Biostatistics for Biomedical Research, Session 3, which is our fun session on statistical graphics and statistical tables. I'm really glad you're here, and I'm just going to check. Well, good morning, everyone. I want to welcome you to the Biostatistics for Biomedical Research, Session 3, which is our fun session on statistical graphics and statistical tables. I'm really glad you're here, and I'm just going to check. Well, good morning, everyone. I want to welcome you to the Biostatistics for Biomedical Research, Session 3, which is our fun session on statistical graphics and statistical tables. I'm really glad you're here, and I'm just going to check. Okay, I hope this is fixed now, and moderators, if you can let me know if otherwise. So the chat line is for questions that you have that are short, that come up during the session. If you have questions about earlier sessions or after this session is over, please go to datamethods.org. So I'm broadcasting today from the beach. I'm on vacation, and so I'm using a different setup than I normally have. So please bear with me with any technical issues. I hope it's not too much of a problem for you. So we're going to go right into the material, which is our material on graphics in chapter 4 of the notes. And the start of the material points you to some very important references. And the gold standard reference for scientific graphics is The Elements of Graphing Data by Bill Cleveland, which to me is a book everyone should have on their bookshelf. It's just truly outstanding. This is the real how-to of scientific graphics. There's lots of other books that are really beauties, especially books by Edward Tufte, but the Cleveland book is the how-to book. And then I have a click here to an audio by John Rouser that you should have viewed already, hopefully. This is really an amazing video that really overviews Bill Cleveland's philosophy in a wonderful way. So I highly recommend that video. We also have a full graphics course that's motivated by Bill Cleveland and his colleagues. And that is a link to here under Staff Graph Course. And we have a special link with resources for clinical trial graphics, clinical trial reporting. Now, Paul Murrell has a wonderful summary of recommendations. It really captures the essence of Bill Cleveland. And so they're listed here. Display data values using position or length. That is really how the human eye best perceives things. And so lots of experiments have backed that up. Use horizontal lengths in preference to vertical lengths. And so if you were going to use a bar chart, which is highly not recommended, you want to make your bar charts be horizontal instead of vertical. We read those more accurately, But more to the point, you can have longer labels describing the categories when you make the bars go horizontal. We'll be talking also about horizontal dot plots. Watch your data to ink ratio. That is really important, and Tufte has talked much about that. If your data to ink ratio is not high, that means you have unnecessary graphic elements that are just getting in the way of understanding information. Think carefully about using color because there's a lot of color misperceptions. We don't perceive color orderings very accurately, and a good many people are colorblind. Do not use areas to represent data values. Please do not use angles or slopes to represent data values. So areas, an example of that would be um, a bar chart. Um, Angles or slopes, the example there would be pie chart. Please do not use volumes to represent data values. This is a real problem in perception. Example of that would be an exploded or three-dimensional pie chart. So on the point about not using areas, it's not a good idea to use a bar to represent a single number. A bar has 2 dimensions and a single number only needs 1 dimension. So the bar uh, uh, width has no information, it just gets in the way. Now, the software you use is really up to you. I will just say R has pretty amazing graphics and it has multiple graphics models, and that's really the only downside to R is there's so many ways to do graphics that you can sort of get lost. And so you have base graphics where you have a lot of control, but you have to do more work. And then there's an older package for more advanced and multi-dimensional graphics called Lattice, which is fast, but it's not quite as clean in some ways as the ggplot2 package, which is very flexible, and it has the nicest defaults. For semi-interactive graphics, which we'll talk about today, these are graphics that you insert into HTML reports. The rPlotly package is really incredible. And it uses the Plotly system, which is a JavaScript library that uses a really standard JavaScript library called D3 that's super powerful. So there's a link here for getting started with Plotly graphics in R, and we'll give you some examples of that. And then there's the fully interactive graphics, and for that we use RShiny. And RShiny is very, very powerful. It takes a little more programming, and also it takes running a server, so you might not be able to view the graphics when you're flying on an airplane, for example. Now there's lots of nice cookbooks to help get you started with R graphics, especially with ggplot2. Now the models that most people use are really aimed at producing nice printed output. And we're starting to see printed output using PDFs, for example, PDF documents. That's starting to be superseded by interactive graphics. And there's a big advantage of interactive graphics because you can present more information, but not all at once. So you might decide what's the most important thing to present. And then you might have hover text such that when you hover the mouse, you see more detail, but the detail doesn't get in the way of the main message. So we'll see examples of that. And then there's sort of a diversion here to remind you that you really want to present raw data whenever possible. If you present transformed data or data that somehow collapsed, sometimes you'll miss something very important and sometimes you'll be misled. So here's an example just showing spaghetti plots using this data set that you can get once you install the HMIS packages. This is the cervical dystonia data set that you see obtained here with the getHData function in the HMIS package. And then we're using ggplot, and we're separating patients out by their patient ID and by the site that they happen to be seen at. So there's 9 clinical sites. These are just kind of arbitrary divisions, just so we don't have too many strands of spaghetti on any one plot. And then we have different colors for different patients. So this is just an example of serial or longitudinal data. the x-axis is week after randomization, and you can see shapes of responses in individual patients. And it's very important to note that every patient starts at a different point in terms of how much symptoms they're having on this Twister's total score. I see a lot of longitudinal data, especially with animal experiments, where every animal starts at the same point. And that is very misleading, and it helps you to not understand your data. And so if every animal starts at the same point, that means you've normalized the data by dividing all of the measurements by the measurement at time zero. You really don't want to hide the baseline variability. You want it to be fully there. So the message here is just show the raw data. Now we get into graphics for categorical variables. Of course, everybody knows about the evils of pie charts. And not only do they have a high ink to information ratio, but they have optical illusions. That part is less well understood. In other words, if you take a pie chart and ask people what the biggest category is, if the biggest category is not like twice as big as the next biggest category, if it's a close call, people will tell you a different category is the biggest category depending on your angle of rotation of the pie against the horizon. The horizon has a special reference meaning for us. And so since it has an optical illusion and it depends on the rotation, that's really reason enough to never, ever use pie charts. They're also hard to interpret if you use subcategories. I'm sorry, I'm getting ahead to the bar chart. It's hard to label categories when there are many of them in a pie chart. The next worst chart is a bar chart. It has a high ink to information ratio. It's hard to depict confidence intervals, and we usually see one-sided error bars, which doesn't make a lot of sense. Hard to interpret if they're subcategories. Labels are hard to read if the bars are vertical. And then you have a major improvement on the bar chart due to Bill Cleveland, and that is the dot chart. The dot chart leads to very accurate perception. It's easy to show all the labels, and there's no caption needed, and it allows for multiple levels of categorization. So here's an example where we're using the Titanic 3 data set that's associated with the HMISC and RMS packages. And what we're showing here is frequencies, how many passengers are in different categories. So there's no outcome variable here. The outcome variable for Titanic would be, did you get on a lifeboat or not? But we've divided the data by sex of the passenger, by the passenger class, and by 5 groups of age. And this is really a terrible, terrible way to handle the age variable. So we're just showing this as an example. Don't repeat this mistake. So this is going to hide a lot of variation, but the age intervals are chosen to not hide too much of it. So we're stratifying the data by 5 intervals of age, passenger class, and sex, and just reporting the frequency, how many passengers are there in each category. So that's a pretty nice use of the dot chart. It's especially nice for the categorical variables that did not start out continuous like the passenger age. You can have multi-panel dot charts, and we can arrange lines of dots vertically within a panel, and we can sort various ways. This is a special dot chart for comparing treatments in, say, a clinical trial. And this is a kind of bubble plot. And so the size of these points, you see, goes with the sample size for each of these cells. And we're doing separate stratification. So the x-axis is the proportion of subjects that are in each category. So that's on a common scale. So you can scale all of these on a common scale because we're stratifying by race. Then we're stratifying separately by sex. Then we're stratifying separately by which exclusions the subject had in a trial. And we're stratifying by Europe versus North America. So we have a lot of stratifications going on. We're stratifying by treatment always and by region always. And then we're stratifying by different categories. And so you see treatment B is the blue triangle. treatment A is the black circle. So that's just another example of a dot chart. That's one that's not hierarchical because it's using separate stratification here. So the way you read this is um, what proportion of the patients in North America uh, were Asian, so, and who were in treatment B, and the same for treatment A. So that's just another kind of multi-way dot chart. This is a special dot chart when you're reporting lots of binary outcomes, and these could be adverse events in a clinical trial. And so the x-axis here is just the proportion that have that at least one of those outcomes over time, like the proportion that ever had nausea in treatment A, the proportion that ever had nausea in treatment B. See, it's much higher in treatment B. And then you have the categories of the adverse events going vertically. And these adverse events are sorted in order of the difference in the proportion. So you see you have a big difference here, and when you get up here, you have a small difference. So the way you sort these categories, by sorting by another metric here, the difference in two proportions, you can make more sense. So if you wanted to concentrate on the adverse events where there's more of a difference, you could look down here. Now that difference is actually computed here, and so we have an example of showing the same data two different ways. And you can see this is sorted by the difference, just as this is. And now we have the difference, and we have the 95% confidence interval for the absolute risk difference. So by having two different panels here for the same variables, you're able to show a lot of information. And those of you who have looked at drug study reports and look at table after table of adverse events will recognize that you can see patterns much quicker and more clearly using this graphical presentation. Now we get into displays for continuous variables, and there's a note here of avoiding chart junk, which Edward Tufte has preached about a good deal. You don't want to show dummy dimensions in bar charts, rotated or 3D pie charts and the like. Now, what happens when we get into continuous variables? Well, let's start by plotting raw data, and let's investigate what it's like to plot raw data for two continuous variables when you have lots of observations. So this particular data set has 136,000 observations. And when we plot the scatter plot, you can see that there's a lot of information here, and we see pretty good agreement between the two pH measurement devices. You know, they kind of go along the 45-degree line, although there's a systematic lowering here. But you really don't get a notion of the collisions of the data points. So there's a lot of collisions, and you don't really get a full feeling for the frequency distribution in here where there's lots of collisions. So we have a couple of different ways of dealing with that. One is hexagonal binning. And when we do hexagonal binning, we can use little bins. This is actually using dots instead of hexagonal binning. But we use these little bins. So let's say we have 100 or 200 bins in each direction. And then we can control how the bins are set. And so most people let this default, but we can take control over how the bins are set according to the frequency of data point collisions. And so say this color here is associated with combinations, XY combinations when there were 5 or 6 observations tied at that point after binning. Here's a color where there were exactly 7 observations. So when there's only one or 2 or 3 or 4 observations, we give those their own color. And then you can see where the color is bright here. It's where you have a very high density, where there's between 488 and 3,400 coincident points in these little bins here. So you can do the same sort of thing with hexagonal binning. So this is a way to handle large data sets. Now, what about showing entire distributions? Continuous variable serum bilirubin. This is continuous variable albumin. We stratify it by treatment, and we have the empirical cumulative distribution function. So this is really a gold standard for presenting overall distributions when you don't have covariates and you're just stratifying by a few things. Here we have two treatment groups. So red is placebo and black is the D-penicillamine, and you're showing everything about the distribution, all the quantiles. So the empirical distribution at a given point X is just the proportion of subjects that have an X value less than or equal to that point. And so that requires no binning whatsoever. It's a full information display, except for not adjusting for covariates. So it's a very excellent way to show continuous distributions. This is a box plot, but it's not the standard box plot. Here we're stratifying by the disease diagnosis and looking at the distribution of serum creatinine. And we got sample sizes listed here. Now we're showing the median, and then the mean is the dot, and the interquartile range is the standard box. But we're also showing the 0.05 and 0.95 quantiles, so that's out here. So we're actually showing information a little bit better than a standard box plot. And as you'll see in just a second, you'll see more quantiles can be shown. So this is a schematic of an extended box plot. You see we have the mean, we have the median that splits the data into half. Then we have the interval here, these quantiles 0.375 to 0.625. That is a quantile interval that contains 1/4 of the data. Then you have an interval that contains half the data. That's your usual box, interquartile range. Then you have an interval that contains 3/4 of the data. That goes from these quantiles. Then you have an interval that contains 9/10 of the data, and that's the outer. And so that is from the 0.05th to the 95th, 0.95 quantile. So extended box plots show a lot of information. They don't work well when you have a lot of ties in the data, and they don't really show by modality. That's a big weakness in a box plot. But here we stratified by above and below the median waist circumference, I believe, and by male, female, and we put age into quartile groups, which is a very poor way to display age, as well as a poor way to display the waist circumference. But we're categorizing that just to get it into a multi-plot format. That's hemoglobin A1C is on the x-axis. Now this is a better way to show continuous distributions versus other variables. These are split or back-to-back violin plots. So a violin plot is just showing the data density, and you can see there is increased data density in here, and that is for treatment A, and the blue is for treatment B. And then you have this over time. So you can see some asymmetry. Sometimes you see a little clump of observations out here in this case, the right tail. The plot gets very faint when there's not enough observations to really trust the density estimates. But if you look at each half of this violin plot, it's just a smooth estimate of the density, which is a smooth version of what a histogram is trying to estimate. So that's pretty effective for longitudinal whole distribution types of plots when you have two treatment groups. So that's called a half violin plot. Now we get into plotting the mean of something as well as the difference between groups. One point that Bill Cleveland has made over and over is if you want to show someone a difference, you actually need to calculate the difference. And you need to make your confidence interval to go with the difference and not with the individuals. So these individual confidence intervals may not be as helpful as the confidence interval on the difference between male and female. But you see here that we have the standard mean and say, I think these are bootstrap confidence intervals for the mean. That's red along this axis, but we have a second axis, which is on the same spacing, but it's got a different center. So here is 0 on the difference scale. So you can read the difference on this scale, you read the raw means on this scale. So that gives you more information. Now we come back to the notorious bar plots, which we call dynamite plots because it looks like the handle you're pushing down to detonate the dynamite. And so these things are really not well defined and they have a lot of problems, including optical illusions. The human eye does not read the error bars. Uh, the human eye sort of adds the height of the error bars to the height of the bar as you go across. And that creates an optical illusion when you're just trying to read the mean. But you can see that the two-sided error bars or confidence intervals, depending on how you're doing it, can get kind of hidden in here because it's an asymmetric way to present data. And then it makes this arbitrary choice of an origin. And it's really unclear where the origin of a bar should be. Should it be at 0 on the scale you're using? Should it have been something up there because you don't see values down at 0 for that particular variable or the person would be dead? So I think bar plots have a lot of problems, and they also tend to make it unclear whether you're using confidence intervals or you're using standard errors. So there's really no reason to do that, and there's a lot of reasons to show the raw data. So these are just some examples of how to replace bar charts with more informative displays. Now this one over here, for males, non-current smokers, we have a box plot, and then there's outer quantiles that you can't see very well with some other lines that go further. But you have the raw data points shown here. There's not enough data points in the current smokers to show the box plot. That's why it's not plotted here. But the mean is with a diamond and the median is with a vertical bar here in the middle. So instead of a box plot, show the raw data when you don't have a big data set. That's the message here. I think even better is a spike histogram that we'll get to shortly. This is just using a symmetric violin plot to show the distribution as well as showing the raw data, instead of just showing some big box that really is devoting a lot of territory to your graphic, and it only displays one number. That's a pretty use of space, pretty poor use of space. So now we're getting into the semi-interactive graphics examples. I think this is really the way of the future. So let me try to shift to this other window. Just take me a moment to find this window. Okay, so these examples were produced using either ggplot and the ggplotly function in R, or going directly with Plotly. All the latter graphics will be using rplotly directly. But you see, these are spike histograms, so these are really high information displays. And instead of using a bunch of dots to represent raw data and then offsetting them so they don't run into each other, you just have the height of the bar is proportional to the frequency after you do just a little bit of binning. So I usually use 100 or 200 bins, and you can see a hover text when you hover the mouse. So you can see this is a value of 10.1 for pro time, and at that point there were 22 observations. And so you can see where you are. Every variable is on a different scale, so you don't have an x-axis for these variables, but you read the x values by just hovering. So this is an SGOT value of 70 where there were 14. But you get a lot more information because if you go over to the leftmost point of each histogram, you'll see a lot of summary statistics, and you'll see the full label for the variable and the units of measurement. So alkaline phosphatase, we're looking at 312 observations overall, and we have 106 missing values. There are 295 distinct measurements, distinct values. The information quotient is 1. That means this is a truly continuous variable. The mean value is 1983. The Gini's mean difference is 1760. We talked about that in the last session. So that is the typical difference between any two patients. in terms of alkaline phosphatase. And now we have the 0.05 quantile all the way to the 0.95. So you see the hover text can give you any amount of information on any of the variables. We're also encoding the color of each tracing with is proportional to the amount of missing data for that variable. And that's just another way to bring information to the chart. I want to pause just a second to see if there were any questions coming through. And right now, I don't think I have that activated, but I'm going to rely on the moderators to tell me if there's anything that we should be addressing from the last section. So please don't hesitate. So those are spike histograms. This is just dot charts, and we're able to interact with the dot chart to see more information. So when you see the dots now, this is stratified separately by histologic stage, and then we stratify by sex, and then we stratify by the presence of the symptom spiders. And what you have in each interval, in each dot, is the proportion. This is stratified by 3 treatment groups: deep penicillamine, placebo, and not randomized, that you see on the right. And then when you hover over a dot, you can see we're currently in the non-randomized group. 0.05 of them were in Ludwig's criteria 1. And that 0.05 represents 5 subjects out of the 100 subjects who were not randomized. So by hovering, you see all the detail that you see, and we've learned the hard way that you just always want to give the numerator and denominator because somebody's always going to ask you what they were. So that's just a dot plot, and that's produced with a summary M function in the HMIS package. And R, the capital M just means multiple types of variables, including categorical and continuous variables. For the continuous variables, we're saying to plot the continuous ones here, and for the first 4, these are extended box plots. So now instead of giving a key or legend, you just hover. So you see that if you hover over the, and at this magnification is a little bit hard to hover over exactly where I want, but see it says Q.5 equals 3.565. So that is the median, the Q.5, the 0.5 quantile. And if you go over another point, you see this is, we're in placebo still. Q.975, that's the upper quartile, and that's 3.83. And Q sub 0.95 is 4.1. So with the interactive graphics, you don't really need to explain so much because you can explain it on demand. So you just encode in your hover text, which is extremely easy to do with Plotly graphics, and you can do this with ggplot using the ggplotly function usually. Just have the explanation whenever you hover, and you'll see what you want there. And so I really encourage you to think about that instead of having a lot of explanatory information separate from the plot. Now, this really also leads into what would be a much too long discussion, which has been discussed very much on Twitter, is what is our publication model and why do we still use paper journals? And I'm one of those radicals that think we ought to get rid of journals. And the restricted formatting is just one of many reasons besides predatory financial model and so on. But when you get away from the printed page, you can see that the interactive graphics have a lot of advantage over the static graphics that we've been forced to use for journals. Now this is stratifying data by disease group, and this is a great example of how you really get more information with spike histograms than you do with box plots, because you notice these distributions are all bimodal. So this variable that we're showing here is mean arterial blood pressure, and we're using 200 bins, And then we have our frequency of being in each bin for a data set that has about 10,000 patients in it. Now with Plotly graphics, you can turn off these things. So I can say turn off the histogram. So when I turn off the spike histogram, I have the quantiles. This is like a box plot, but it doesn't really need a box to show the same information plus more of what's in a box plot. But when you have the raw data, you see a lot more than the box information is able to show you, because you see bimodality that's completely hidden with a box plot. These are bimodal because the way these measurements were taken is the nurses were instructed to record the worst blood pressure in a 24-hour period for these critically ill patients. And the worst blood pressure could be too low or it could be too high. That tends to shift them out towards the extremes, creating this bimodality. So that's spike histogram, and then you have the mean here. I'm going to just try to shrink this a little bit and see a little bit more. And then there's a way to show other information, which by clicking on the Gini's mean difference, there's a little bar that came up over here. See that the length of that bar is the Gini's mean difference. And if you turn on the standard deviation, you'll see, it's a little bit hard to see here, but you'll get a second bar. The length of that is equal to the standard deviation. So you can show a lot of information. You can turn off the quantiles, you can turn off the median, turn off the mean, and show just the histogram. So you have a lot of flexibility. And then when you hover over something, you'll see the detailed information. So we have some more examples. This is a real effective use of survival plots. These are just 1- Kaplan-Meier estimates. And it's really recommended that you don't plot Kaplan-Meier estimates that go down, but plot cumulative incidence estimates that go up. And there's a very simple reason for that, is that journals often have a silly rule that when you're plotting Kaplan-Meier estimates, they have to go from 0 to 1, even if your survival goes from 0.95 to 1. You have a rare outcome. And when you turn it around and show cumulative incidence plots, the journals don't have a rule, so you can use a reasonable upper limit, like 0.8 here of the cumulative incidence. But what this really also does for you is to make use of the fact that the number at risk is really a continuous variable. We tend to show the number at risk at, say, yearly intervals, but when you hover the text, hover the mouse, you can see we're currently at 4.6 years after randomization, and the probability of having an event by that time is 0.48. The number of subjects at risk at that point is 36. And so when you go across, you see the number at risk just goes down. Here's number at risk is 9. And it says the probability of having an event by 9.432 years is 0.776. And it says also for t equals 10. So the plot was flat at that point. So the cumulative incidence estimate extends out to 10 years. It's also 0.776 out to 10 years. But you see the number of risk, you can get that at every possible time. So you don't have to decide on the resolution for putting the number at risk at the bottom of the axis. And then this is a very important note. You can show the right confidence interval when you're using modern software. So the confidence interval you want to show in a randomized trial is never the confidence interval for the individual treatments. If you want that, you can turn that on. I just don't have that on by default. So that's the confidence interval for an individual treatment, or individual group in this case. It's not treatment. But that's really not the confidence interval you want. And if you turn both of those intervals on, you see everything gets really messy. That's when you're comparing treatments, you don't want the individual confidence intervals, because those can overlap and there still be a significant difference between the two treatments. And also a randomized trial is designed to estimate differences. It's not designed to estimate, to make statistical inference for one treatment arm at all, because you don't make random samples from that one treatment in a population. So this is a confidence interval for the difference in the two curves. It's centered at the midpoint. And the width of this is half the width of the confidence interval for the difference. So by using half the width of the confidence interval for the difference in these 2 points, that has the property that the shaded band touches these 2 curves if and only if there's a significant difference at that particular significance level. Now, when you hover over, you'll see the more information. We've already been through that. And you can turn off the confidence interval for the difference if you really want to, and turn on the other ones. But I really recommend this to be used as the default. It's also much less busy in the plot. So I know you're not used to seeing it, but this is really the way we should present most confidence intervals when you're comparing 2 groups, including confidence intervals for a simple difference in means. Let's see, this is an advanced table we're not going to go through right now. And then there's a section here about clinical trial reports, and a lot of opinion here and a lot of useful information. So I hope you will look at this as well as the front part of this, which gets you into some example clinical trial reports. And if you, these are the reports that are in PDF format using the old graphics model. And then if you go further, you get into our new R package for interactive clinical trial reports, which is the H report package. And there's some examples you can click on here and call up those examples and hover the mouse and see a lot of useful information. So I'd recommend that you take a look at that. So now we're going to go to back to our notes. I'm going to see if I don't see any new chat there, although I don't know if this screen is up to date. But if we go back to our notes, which I need to find the window again. We just went through a lot of these examples here, and the example clinical trial reports I will leave you to look at. There's also interactive graphics that represent characteristics of people that register for this course. I think some of you have already seen that, and just hover the mouse, you'll see more information. So I would encourage you to take a look at that. So now we go to a bit of a different topic, which is graphs for describing statistical model fits. There's a lot of options here. The RMS package and several other R packages make these sort of things pretty easy to do. And this is where I've found some problems with some of the other packages that don't make this very easy to do. So the really most highly recommended display when you have a statistical model are the partial effect plots. So that's where you show the effect on the response variable varying one predictor at a time, holding the other predictors constant. And we just, for convenience, we set them to the median for continuous variables or to the mode of categorical variables. And then we include confidence bands. So that really is the best approach because it's useful for showing the effects of categorical variables and especially for continuous variables. And the greatest advantage of partial effect plots is it shows the shapes of the effects of the continuous predictors. And then there is effect charts, which are not nearly as good for continuous variables, but this will give you a single number summary plus confidence limits if you really, really, really wanted to summarize an effect with a single number. Now, if you had a comparison of male and females, then that single number might be useful. But we can show differences in means, odds ratios, hazard ratios, fold change, any single number summary for a variable that you can think of, but we typically see these for things like odds ratios and hazard ratios. If a continuous variable is not linear, this kind of display is not very satisfactory because the setting that you make for choosing the interval is going to be very important. So if you have a relationship that's flat in an interval and you choose to show the effect of the variable in that particular interval, the odds ratio will be close to 1. Whereas if you chose points that were in a steep part of the curve, the odds ratio will be very far from 1. So in general, because things are usually nonlinear, and especially if they're not monotonic, these are not so satisfying for continuous variables. I'm really getting away from those now. Nomograms can be pretty satisfying. We'll see an example of that. That shows you the whole model at one time. And so here's some examples where we use a wonderful NHANES National Health and Nutrition Survey data set, and we're predicting hemoglobin A1C using age, sex, race, ethnicity, and body mass index. And there's a side note here that ordinary regression cannot work for analyzing hemoglobin A1C. So there's no way to get a transformation of hemoglobin A1C that makes the variance constant and makes the distribution of residuals be almost normally distributed. The closest I could come would be putting A1C to the minus 1/1.75 power. That doesn't quite do it, but this is a better, it'd be better to analyze this with ordinal semi-parametric regression, as I have a case study in my RMS book and notes. So we're using this transformation here for hemoglobin A1C, and this is the inverse transformation, which we may need. And so we're going to fit ordinary regression onto that transformed hemoglobin A1C, and we're going to have a nonlinear function of age. We're going to have race, ethnicity, category, sex, a restricted cubic spline, and body mass index, just like we do for age, with 4 default knots. Or these are places where the acceleration of the curve is allowed to abruptly change. And so we have here some statistics showing our R squared on that transform scale, showing that we have some very we have a lot of signal in the data. We don't really get anything out of looking at the coefficients, so we really discourage looking at that. We can look at an ANOVA table, but we're going to get a lot more out of plotting the partial effect plots. So this is the relationship between age and the predicted median hemoglobin A1C, holding body mass index at its median, holding the categorical variables at their mode. You can see this is a non-monotonic effect. This would be covered up if you did a regular sort of single number summary. So it turns here. Now this is the inverse transformed predicted value. So when you have something that's symmetrically distributed and you inverse transform it, you're going to be estimating the median. So that's why that's labeled median here. And then body mass index has a non-monotonic relationship, although it's fairly flat here on the left. So this is the effect of changing this variable if you hold all the others constant, and it's on the median hemoglobin A1C scale. This is the effect of moving between the different race ethnicity categories on the predicted median value, holding everything else constant at the median or mode. And this is the effect of comparing males versus females. So this is a pretty good way to show the results of a multivariable analysis. And we really like multivariable analysis because you can take multiple variables into account, whereas the simple descriptive statistics, those are just going to give you marginal summaries, and those marginal summaries, when you don't adjust for the other variables, might actually be misleading. They don't take into account patient heterogeneity. So now we're going to get the single number summaries. I think that is here, yes. So this is on the transform scale. So this scale, which is essentially hemoglobin A1C to the minus 1/1.75 power, is not going to be meaningful to very many people, and you could transform this to give it as another scale. But this is the effect of age going from the first quartile to the third quartile. So this is the interquartile range age effect, is to give you this difference on the transform scale. If you had log transformed it, this would be a log ratio. Now note that this getting these predicted values at the first quartile and the predicted values at the third quartile is definitely not categorizing the age variable. Age is analyzed continuously here. We're just asking for predicted values at two kind of arbitrary ages. And then we're getting differences in those predicted values to estimate our effect and get confidence intervals. Same for body mass index. And then we're comparing the different race ethnicities with a reference group, which was non-Hispanic white. And then we're comparing male to a female reference group. So the next plot is showing a nomogram. And a nomogram is useful when you don't have, say, more than 10 predictors in a model. It can get a little unwieldy. Or if you have lots of interactions in the model, the nomogram may not be possible to draw. But this is a nomogram that's drawn with one command in R. This is the nomogram command in the RMS package. It's probably the longest function I've ever written. And the basis of a nomogram is you just have a convenient scale here to compare to. These are just called points, and they're arbitrarily going from 0 to 100. And that's just so that when you add up points for the different variables, you can add up whole numbers and be pretty accurate. So that's the only reason this is 0 to 100. You can make this any range that you wanted. And now we show the effect of age, starting with the say the lowest age in the data set of 10 all the way to an age of 80. And you can see that the effective age is not linear. You see these tick marks are not equally spaced. So you can see nonlinearity here. And then the fact that this wraps means this is not monotonic. So you actually see a lot with a nomogram, but not as well as in the partial effect plots, because that shows the shape better. But this is where the age curve, remember it was going up and then it kind of took a dip. It was not monotonic. That's what's causing this wrapping of the axis. So the way you read this is if you're at age 50, that would give you about 47 points. You could call those risk points or whatever you want to call them. But an age of 50 will give you about something like 47 points. If you are non-Hispanic white, that's our reference group that gives you 0 points. If you're a male, you see you get about 5 points. So you add the 47 points and the 0 and the 5 points, and that gives you the effects of those variables. And then you add the points that goes with body mass index. And you'll remember this was also a non-monotonic relationship. So you look up the points according to body mass index, add those into the points you get here, and then you get your total points here. So you have to do a manual addition to get your total points. And then this gives you your linear predictor, which is your linear combination of your covariates. This is on that strange scale that made the residuals almost normally distributed and almost equal variance. But then we untransform that and we get the predicted median hemoglobin A1C. I want to ask the moderators if there's to be summarizing any questions you think we should close with as I wrap up here. But I just wanted to say I think nomograms are a very useful educational tool. They make multivariable regression models very transparent. You can actually use them to get predicted values. And one of the beauties of them is once you get one type of predicted value, you can get instantly many types. So in the course notes I have for RMS, you'll see this example worked out in a lot more detail for predicting hemoglobin A1C, in that case using a semi-parametric ordinal model. But it doesn't just have the prediction of the median, but it will have the predicted mean, the 25th percentile, 75th percentile, the probability hemoglobin A1C is greater than 6, 6.5, 7. So you'll see a lot of axes here, and you'll be able to read off those different predicted values instantly once you estimate any one predicted value. All the other predictions come immediately from that. And then we have two quick examples of uh, three-dimensional plots when you have two continuous variables that you want to display. Heat maps types of plots or color heat spectrum are pretty useful ways to describe that. And so we have the support coma score, how much of a coma was the patient in, and then how much of their kidneys shut down. So if your kidneys are not putting out urine and you're in a total coma, your median time to death was 2 days in this study. If your kidneys are working well um, and you're not in any signs of a coma, your median survival time was more than 200 days. Given these patients typically had some organ that was failing, they were all in the intensive care unit. So this is a very effective way to show the relationship of two continuous variables in a regression model. And this other one is another example, and this is using penalized logistic regression to avoid overfitting. And what we're showing here is diastolic blood pressure and systolic blood pressure. And the color here, I didn't put a good legend on here, but the color is related to the risk of the patient having a hemorrhagic stroke if they were given TPA after a heart attack, tissue plasminogen activator. And so the basic idea here is you want to show what happened without imposing your will. So you don't want to assume that the blood pressures relate linearly to the outcome. You don't want to assume that they don't interact with each other. So we're fitting a very general three-dimensional surface to find out if the literature is right that what makes patients have a hemorrhagic stroke after TPA is a high pulse pressure which would be the relationships are along this axis here, the difference between systolic and diastolic, or is the risk really the mean arterial blood pressure, which is this axis? And you see it's the latter. There's a little bit of pulse pressure effect here, but that's running out of data a bit. But the relationship going from cold to hot is largely along the axis of mean arterial blood pressure without superimposing anybody's opinion about how diastolic and systolic blood pressure should have been related to the risk of getting a brain hemorrhage after being given TPA for a heart attack. So that's an example like the previous one where we're showing a smooth three-dimensional relationship, letting the data speak for themselves. And I think that's one of the more effective ways to show interaction and to show how two continuous predictors relate to an outcome. So that is all of our graphics session, and I don't think I have access to the live chat right now, unfortunately, but the moderators didn't tell me anything to be addressing. So I hope that any of you who are watching this that have follow-up questions will be sure to put those on the dedicated topic on data methods, um, um, because the chat will close down shortly after we end this particular string. So thanks very much for joining me. Thanks for putting up with a few technical problems as I broadcast from a beautiful beach here in South Carolina. And I look forward to seeing you at session 4.